Okay, so in this video, we're going to derive the C3v character table. And so first step to do this is we have to identify all the symmetry elements in the molecule and then put them into classes. So first step is determine the symmetry elements. So it's useful to figure out a representative molecule that's of the C3v point group. And so the easiest one to think of is ammonia. This is a C3 molecule, and we have to identify all the symmetry elements in this molecule. And so there's always, every single point group has the symmetry element of identity, right? So that we say by E, that's just the symmetry element of itself. So sort of like multiplying by the number 1. And then we also have in ammonia, we have a principal rotation axis, and that is a C3 axis. So if we rotate across this axis, the hydrogens will interconvert 120 degrees. And so this hydrogen will convert to that hydrogen, this hydrogen goes to that hydrogen, this hydrogen goes to that hydrogen. So there's an element of symmetry there. And we use this hat, by the way, to represent symmetry operations. And so we have identity, we have a C3, and we also have, that's 120 degree clockwise rotation. We also have a C3 twice. And we'll put a hat on there for doing that twice. So that's going to be a 240 degree rotation, very similar to just a C3 one times in terms of how it moves the hydrogens around. And then, of course, if we do a C3 3 times, that is going to be equal to a 360 degree rotation, which is the same as just multiplying, keeping the molecule and all the hydrogens in the same place. So that's equal to identity. So that's not a unique operation. So far we have identified 3 operations. And if we keep going here, we can identify more symmetry operations. There's actually 3 reflection planes. And so these are shown here. These are vertical mirror planes. We use sigma to represent a mirror plane. And it's called a vertical mirror plane with a V, subscript V, because it is coincident with the principal rotation axis. So all these mirror planes contain this principal rotation axis, the C3 axis, in them. And so we call it a vertical mirror plane. And there's 3 of them cutting through the nitrogen and each of the 3 hydrogen atoms. So we're just going to call these sigma V hat with sigma V hat prime and sigma V hat double prime. And so it doesn't really matter which one you call which. And you can see that they're quite similar. And in fact, we have 3 different groups, or what we call classes, of symmetry operations. We have these 3 different sigma V's. And so we're going to group those into one class. Geometrically, they do something very similar. And in this video, I'm not going to get into the mathematical group theory definition of what a class is. But for a lot of these character tables, just intuitively, you can put them in the right class. And in the case of C3v point group, it's very easy to see that all the reflections should be together in one class because they do a similar type of thing. They're going to exchange, for example, this mirror plane right here, it's going to keep the nitrogen and the hydrogen unchanged, these nitrogens and hydrogen unchanged because they're within the mirror. And it's going to swap, it's going to take this hydrogen and put it here, and this hydrogen and put it there. Those hydrogens are looking at each other in the mirror. And all the other mirror planes are similarly just going to swap 2 hydrogens. So this mirror plane here is going to swap this hydrogen, and this last mirror plane there is going to swap this hydrogen, this hydrogen. So they all do very similar things. They're all reflections. They're all vertical reflections. So it makes sense they should be in the same class. We're calling that class 3 sigma V because there's 3 vertical mirror planes in this class. And then very similar idea here with the 2 rotations. They're both rotations. They do similar things geometrically. And so we're going to call this class 2C3. There's 2 different rotations in it. And lastly, we have the identity class. Identity is always mathematically unique. It'll always form its own class. Same thing with inversion. If you have inversion in your molecule, identity and inversion operations always form a solo class by themselves. So at this point, we have our 6 operations grouped into a single, our 6 operation groups into 3 different classes. And so what we can do next is we can actually, I'm going to back up here and just clear some stuff for us and rewrite what we have. And so I'm going to write now our bones of our character table. And we know our character table is always a square in its shape, okay? And what I mean by that is that the number of columns and rows is always going to be the same. And so I'm going to draw the character table here. And on the top left, we always put the point group that we're talking about. This is just the convention of how character tables are written. And usually people put the identity class first. We know we have an identity class, although it doesn't really matter what order you put all these different things. You could put them in the columns in any order that you want, but identity is always put first just by convention. And then we said we had a 2C3 class with the C3 and the C3 twice, and then we had the class that contained the 3 vertical mirror planes. And so those are our 3 columns of the character table. And then at this point, we know that we're going to have 3 rows. And the rows in group theory we call irreducible representations. These are vectors of the symmetry space. We don't know what to call them yet, the so-called Mulliken symbols. There's a naming system of how to name these vectors. But I like to just give them a generic name to start out. I give them gamma. So we're just calling them the Greek letter gamma. Gamma 1, gamma 2, gamma 3. We know there's 3, again, because it's a square character table shape. The number of rows is 3 because our number of classes is 3. Now, the first irreducible representation, the first vector, always has 1s across the board. And so that's just an easy one to fill out as we're deriving this character table here. And I'm going to put another column here just for any sort of functions that later we might want to test to see how they transform. But our first one's always going to be what we call the totally symmetric representation, 1s across the board. You can always do that. And then there's various character table rules that I've gone over in other videos, and we'll continue to describe in future videos. But one of the character table's rules is that the sum of the classes, okay, so what we call the order, the total number of symmetry elements, okay, so here we have an invisible 1, right? And we didn't write it, but there's 1 element. We have a 2 and a 3. So just to add that up, right, that is equal to 6. We knew there were 6 symmetry operations. We call that the order. Okay, it's the number of operations in the point group. It's called the order. And the sum of the squares of what we call the dimensionality, which are these characters, okay, those has to equal the order. And so we're going to end up with something like, well, our first one is 1, because we had 1s across the board, plus I'll just write x, we don't know what it is, this one right here, x squared plus y squared for this last one is going to be equal to 6. And these values here under the identity, the so-called dimensionality, the characters for underneath the identity, are always going to be positive. They're always going to be integers. So they're going to be 1 a lot of the times, 2, maybe a 3, and then very rarely a 4 or a 5, okay? Only in some of the really highly symmetric ones. So, but if it only can be a 1, 2, 3, 4, 5, you can very quickly see that in this case, the only way that this is going to work is if we have a 1 and a 2 as these values. because 1 squared plus 1 squared is 2 squared equals 6. It would be too large if we had two 2's. So at this point, what we can then do is we can fill in 1 and a 2. So we're sort of puzzling this out. And we can use other rules to actually figure out how this works. And one of the other rules, we don't even have to test any sort of vectors at all. But one of the rules that we can any sort of functions, okay, and see how they transform. We'll do that at the end. That's another way to solve it. There's many different ways to solve these. But what we can do here is we can use a principle of orthogonality. So we have a vector, right? And in sort of maybe physics or math notation, we could write the vector like this of gamma equals 1, 1 comma 1 comma 1. And the dot product of now this, okay, so this vector gamma 2, I'll just call it A comma B. We don't know what it is. A here, maybe a B there, is going to have to be equal to 0, okay? And this is one of our rules with respect to group theory. The dot product has to equal 0, but we have to multiply all these components by the number of symmetry elements in that class. So we have a 1 up here for E. So we have to times this by 1. We have 2 up here for C3. So the second component of our vector times by 2. And then we have a 3 up here for sigma B. So we have to times that by 3. So we end up with 1, 2, 3. Just all of those got times by 1, 2, and 3. It was all 1s. Dotted with 1 comma A comma B must equal 0. And if you stare at this for a bit, remember what the dot product is you multiply them all and add them together. So the first component times the first component, 1 times 1, plus 2 times A, plus 3 times B, right? Second component times second component, third component times third component must equal 0. All right? And so the simplest way using ones, which is the way you have to do this. If you have a 1 in the identity, you're going to have 1s or negative 1s usually in your character table. So the simplest way to solve this, we can guess, is that A is equal to positive 1 and B equals to negative 1. That ends up being correct. But there's other ways to confirm this. I'll show you at the end with some functions. And then lastly, we could do the same thing with this last function. So let's now call this C and D, these unknowns. And we do a very similar thing. This time I can go a little faster. We can dot it with gamma 1, which we know is 1, 1, 1, or dot it with gamma 2. They all should be orthogonal, but let's do it with gamma 1. The math is simpler there. So we're going to have 1 times 1 goes up there, and then 2 times 1, and 3 times 1. Again, all the 1s came from here, 1, 1, 1. The 1, 2, and 3 came from up there. Dotted with 2 now, C comma D. And that's going to be equal to, just like we did before, 1 comma 2 comma 3, dotted with 2 comma C comma D, and that whole thing is going to be equal to 0. And so if you look at this and expand this out, right, again, we're going to have 1 times 2 plus 2C plus 3D equals 0. So just working down here, that's going to be 2 plus 2C plus 3D equals 0. And if you stare at this for a while and look at nice integer values that this will work with, you're going to get C equals negative 1 and D equals 0. So you're going to end up with 2 minus 1, 0. So this point, we derived the character table. We can actually give these Mulliken symbol names. And so the Mulliken symbol rules for these, so I can get rid of these gammas now, because we can actually follow the rules. And in another video, I go over all the Mulliken symbol rules. But basically, if you have a 1 here, you're going to give it an A or a B. And you give it an A if you're symmetric with the principal rotation axis. What's the principal rotation axis? There's only one rotation axis here, it's the C3. What does it mean to be symmetric with? It means you got a 1. So you're symmetric. So you give it an A. Both of these are going to be given A. You give it a B if these were negative ones, if these were anti-symmetric. And then you go to a mirror plane. And the only thing left really we have to look at is here. And if you're symmetric, you give it a subscript 1. If you're anti-symmetric, you give it a negative 1. So those are our mulligan symbols for the first 2 irreducible representations. And then when you have a dimensionality of 2, you give it the symbol E, which is a little bit unfortunate. This E is a mulligan symbol. This E means the identity class, but those are different, okay? This one's an irreducible representation referring to the vector 2, negative 1, 0. This one is referring to the identity operation, which is in the identity class. Remember, the operation has a hat, the class doesn't. So lots of nomenclature here. But so that's the end of figuring out what the table looks like. Now let's just do a check. And so I just wanted to show you, if you just pull up online a character table, what you get. You can see we derived all of this. You can see they put Z here. Z is defined as the principal rotation axis. So nothing special there. But if we work through this, we can actually check some of these results. So for example, the function Z, we could figure out how this works. So let's consider the ammonia molecule, and I'll sketch one out here just so we have something to look at. But if we sketch out this ammonia molecule, right, and we think about, okay, here's our principal rotation axis. We define that always as our Z. What is going to happen here? Well, if we have a Z vector, that's what we're thinking about. We're thinking about how does this function Z transform with all these different operations? Well, if we take the operation E, right, hat, because it's an operation, well, the identity operation always takes a function and takes it into itself. So Z just goes to Z. And if we think about the matrix that represents that, that would be just a 1-by-1 matrix with a 1, right? That takes Z into Z. And we take the trace of the matrix with the sum along the diagonals, and that's how we get the character of the matrix. We use this symbol chi just to mean character. But the character for E is therefore going to be 1. And if I do the same thing for C3, now this gets a little bit more interesting. And we actually have to use a rotation function here. And so and the reason why we have to do this is because when we go into X, if you imagine, well, actually we don't have to do this quite yet, but if you imagine the Z vector, we're going to be rotating this 120 degrees. So imagine you have the Z vector and you're spinning it 120 degrees with imagine you have a piece of string and you're spinning the Z vector. That's actually not going to change that Z vector at all. So, in that case, Z is still going to go to Z. So again, you're going to get your character for C3 hat equals 1. And the last one here is your mirror plane. And so let's draw one of the mirror planes. You can use any mirror plane you want, any of these functions. But there's a mirror plane, for example, cutting through any of the hydrogens. So let's just draw the easiest one that's there is to draw in the plane of the presentation. That takes this hydrogen into that hydrogen, right? It's going to swap those. It's not going to change this nitrogen. But we have this Z vector here, and that Z vector is not going to change. It's in the plane of the mirror, so it doesn't change. So again, for the sigma V operation, and you could test this with any of the different mirror planes, they're all going to have the Z vector in that plane. So Z is just going to go to Z, and the character of sigma V is going to be equals to 1. So what that tells you is that the z function transforms as 1, 1, 1. That's actually a way you could derive a1. I told you earlier, hey, the first one's going to be totally symmetric. It's going to be ones across the board, but you could actually derive it. So deriving these other ones, rz and x or y, or rx and ry, or these quadratics, those are a little more complicated. So let's take a break here and I'll tell you how to do that in the next video. But you didn't even have to do it for this one. You could just puzzle it out. You didn't even have to do that. For some more complicated character tables, you might have to use the functions to help you derive some of the irreducible representations.